Hi, this is Jeanseong Baik from Hanyang University. This time I'd like to introduce some minimal work of resilient system targeting the electrical driven vehicles using task migration with a network-centric approach. Now, shall we start? So I'd like to start with a vehicle. Due to the rise of the autonomous vehicles, nowadays more safety assurance is essential. And still, we're not even close to guaranteeing safety for such a technology. This is the status quo. Whenever a new cause of an accident appears, we get to define the cause a long after the accident and give a solution a long after the definition, and the solution is distributed a long after the solution has appeared. Unfortunately, this is the normal cycle of handling the error. It is impossible to predefine the unknown errors exactly. But to change this paradigm, instead of predefining the error in a situation, we can try to neglect any situations that could happen and concentrate on constructing seamless services. In this manner, we use task migration method to maintain the essential complex information, and with the network-centric approach, we could reduce the hardware cost, ensuring safety. The sudden unintended acceleration is one good example of a vehicular accident. Let's call this SUA. Suppose three vehicles driving in same speed, and the middle vehicle suddenly accelerates. This is an unintended and uncontrolled acceleration of a vehicle. So what is the cause? Is it the driver's fault? It might be, but we try to concentrate on the cause that is responsible for the systems, which is caused by the control failure of an ECU, which is an abbreviation of electronic control unit. Whenever the driver gives some amount of pressure to the accelerator, the ECU converts the pressure to an electrical signal and successfully drives. But at that time, the ECU didn't work as intended. Let's look at the vehicle in detail. There is a motor engine and an accelerator, but what sends a signal to an actuator is, as I told, the ECU control unit. Not only there is an ECU for a motor engine, also there is an ECU for entertainment. We can listen to music or something. We can rank these ECUs in two levels. One is a critical function and another is non-critical function. This is one basic control system. We can view safety and cost like this. Initially, the safety and cost are the least as possible, but if we're driving a car, of course, safety is important. So we have some safety standards to satisfy. How do we satisfy the safety standard? By multiplying the ECUs that enables the system to take over the function whenever the primary ECU is corrupted. But not only the safety, but the cost is also raised, which makes the vehicle not being affordable to buyers. Therefore, the vendors should lower the cost as well as maintaining the safety assurance. Does it seem possible? Okay, let's talk about this now. In this slide, we can see a conventional structure of a control system using redundancy. Suppose there are exactly two ECUs for each function. The total number of function is n, and 2n is the total number of ECU. By mutually connecting the ECUs and the sensors, we can make consensus between them. And without redundancy, each function can be taken over to neighbor ECU whenever the primary ECU is corrupted. But not all ECUs can take over the function. We have to check two main things. First, can the destination ECU take over the function? Second, does the destination ECU have enough capacity to run the function? This is the implementation of a Lego vehicle. In the right side, we can see a picture of Lego vehicle consists of two ECUs that are driving some different functions which are monitored by the central ECU. And the left side is the overview of the connection between ECUs and actuators. When each ECUs are handling their own functions with single point connection, it would cause single point of failure. But with a little bit of wiring between these neighbored ECUs, which is much more cost effective than the additional cost of an ECU, the system can handle each ECU's failure and map the mission to another ECU dynamically. In this vehicle, we settled these motors additionally wired with the other ECU, which was handling other functions in the vehicle. These connections seem simple and applicable to actual vehicles because ECU's resources are not that different from the testing environment. This is the result, the timestamps of speed of the monitored ECUs. The source ECU was handling the drive function, which was driving in 100 RPM, and suddenly an acceleration occurred by the failure of the ECU. The central ECU immediately cuts off the controllability of the source ECU as soon as the SUA is detected. And the central ECU routes the migration to capable destination ECU. Well, there are some procedures of migration, such as dump the memory, copy the dump file through the network, and restore the memory from the dump file. And it took a few seconds, leaving the vehicle uncontrollable, but in this example, the vehicle was able to migrate and converge to the previous state successfully before the vehicle has totally stopped. Task migration is not a preferred resilient method in real-time systems, but it has shown possibility by trying to minimize the size of the dump file by using partial migration method, which was able to pick up only active and essential data reading from the process memory. This is what the vehicle results would look like after applying these methods. For now, the drive function is mentioned to maintain the speed and direction and so on. But in the autonomous vehicles and platooning scenarios, the more functions are expected to be managed. After all, our research methods are more expected as functionalities of the vehicles get more complicated and plentiful. Finally, I'd like to conclude. We successfully implemented a Lego vehicle avoiding the sudden unintended accelerations. We proposed a practical method to overcome the limitation of single point of failure without totally underlying in redundant system. And there were some contributions by collaborating task migration method and under consensus network-centric approach. First, the migration method maintains the detailed states of functions. Second, the connectivity of neighbored ECUs were able to dynamically take over the function as soon as the failure occurred. And it is cost effective because we can reduce the redundancy by connecting the dots. This is the end of the presentation. For any after-all contact, please email me with the address shown in the slide. Thank you.
May I ask one question?
Yes, sir.
Yeah. I just wonder, did you use some real traces to validate your findings that let's say, I see your very good motivation, but I don't know whether you have justified using the experimental data to do the simulation or real testbed study.
The testbed is restricted only in the Lego vehicle, and this Lego vehicle is has shown the possibility for a real example, and it is a little bit far from the actual vehicle, but we're planning to expand this research to some actual test bed. So this is yes, sir.
Dummy vehicle. Okay. That's still interesting. I think road safety, considering the electronic unit, is different from the traditional study. Only look at the let's say road situation, but now is in car electronic unit problem. Okay.
Yes, sir. And
Francisco, who is chairing the session? I don't see the session chair. Maybe you can chair this, maybe.
So basically, as far as I know, there is no one chairing the poster sessions.
I see.
So
it's interesting.
So I think that like when every poster or demo presenter has its own slot, and then in their slot they should present themselves, show their work, and then there should be like time for the QA. So that's all I know for now. I will let you update it if I have news about it.
Sir, I didn't catch the question very well. Sorry, can you tell me if I have to answer something?
No, for now, no. I don't have any question from my side. I'm just saying that if someone wants to ask you a question, it's free to do it.
Yeah. Yes, sir.
Hi, this is Vincenzo Mancuso. I'm one of the organizers of this session. I would like to see one slide which is representative of your work, because I was watching another parallel track while you were talking, so I had no idea what you presented.
So you want to see the slide?
I would like you to keep one important figure, something representative of your work, always on the screen, so that people like me jumping in will understand what you are talking about.
I think the connection. Sorry for
there is an echo.
I think there is some communication. So now I can hear and.
Yeah. Okay. Can you hear me?
Yes, sir.
Okay. What I was asking was exactly a figure like this, so that if someone changes track from one poster to another in parallel, when it jumps in here, we'll see what you are doing and we'll ask. So now I didn't attend your presentation because I was talking to someone else in a parallel track. You know, there are 4 parallel tracks. So like in a real poster session, people will pass by and stop. This is my idea, and this is what we described in the instructions. So now that I'm here and I'm interested in this vehicular protocols, Can you explain me if you use some direct vehicle-to-vehicle communication rather than go through the cellular network for avoiding impact?
So I think this slide is the proper slide to present. This is minimal work used only restricted using the Lego vehicle, and our research team is trying to expand it to a CAN communication, but for now this uses UDP communication, and it is alike with the broadcast communication used in the CAN communication. So this is alike the vehicle communication, but not exactly the same. But the mechanism is the same.
Okay, I see you use Raspberry Pi and you use a Wi-Fi router, correct?
Yes, sir.
So this means that you are not implementing vehicle-to-vehicle communication. You go through an access point. That's fine. That's correct. But I mean, it's one of the possible options. Not the only one.
So, yes. So this has some contribution that the possibility between the ECU's migration, and we supposed that the communication is naively alike. So we didn't see that as a problem at first. So, but after all, there's a need to expand to vehicle-like communication, V2V communication. So this is not a V2V connection. It's an intercommunication between the ECUs inside the one vehicle, single vehicle.
Yeah, it's a single one. Yeah, now I'm getting it. Yes. I see. What's the time budget that you have for task migration? I mean, how fast can you migrate, and how fast you should migrate?
There was some network delays, so actually we have to compare with some other baseline, but this is not a vehicular. See, so in this slide, we presented the timeline that presents the migration. But,
so what are the units here? You have time in seconds, and then you have the speed in, what is this? RPM?
RPM, yes, sir.
Okay. And okay. Okay.
So if we have much more plentiful resources to expand this to another system, if the vehicle system is still Linux alike, we can simply port the applications to the system. And this is not the delay with our method. It's just a delay from the Lego vehicle and the Wi-Fi network connection.
Yeah, but my question was more like, do you really need to migrate within the vehicle, or because you don't have much time to migrate, or maybe you can migrate to some external server given that you have a time budget maybe of half a second or so. So you may migrate your functions to some node which is outside, but which is much more powerful. Is that a possibility in your case or not?
So the reason that we didn't migrate to an outer node is because we tried to speed up we tried to construct a seamless service that just looks like it hasn't been a problem. And
okay, thanks.
I don't know if this has been a right answer.
Yeah, I think so, but of course I need to read more. But thank you. I appreciate your answer.
Thank you, sir.
Okay, if anyone else wants to ask, please feel free. There are still a few minutes. I'll jump to another channel. Talk to you later.
Sir, so so is there any question?
Each session is only one speaker or multiple speakers? For the poster session, yeah.
I think that there are now another 2 posters after this poster.
Okay. Can you go back your slides earlier to earlier slide about the method?
About the method?
Yeah.
Which slide do you?
Previously. This one is the hardware system. Next, yeah, this one is okay. Next.
Shall we go next?
Yeah, this one. Let's see. Let's see. So you have a front end, some electronic device, and back end, some other device, and the sensors are external sensors. These 2 sensors are external, or the bigger are the sensors to the outside situation, like the checking the road and other vehicles and such things, or the in-car sensor to look at the driver's behavior.
These sensors are internals.
Okay, looking at the driver's behavior or their pressure or something.
Yes, sir.
And you are aiming for a high level of automation, autonomy, right? Autonomous driving. You wanted to level which type of level of autonomous driving?
So I'm targeting the plentiful functionalities with the autonomous vehicle. Yes, that's right.
Sounds good. Yeah.
Sorry, I also have another question. You mentioned that you're going to dump and copy the state of the failed controller, but my question is, what happens if I mean the first controller is actually failed, so we don't have the opportunity to dump the data? What happens in this case?
Oh, so in that case, we have to restart from another ECU. So it's still connected, but in case that the situation you mentioned, then there's no possibility to migrate. And I agree with that opinion. And that is one thing, one minimum thing that we can do. Just restart from another system. But also we can pre-check with the mixed critical schedulability during the migration from the destination ECU. So there are two options, I think.
I see. Thanks.
Thank you. So if there is no more questions, I think I can. Should I end up the presentation?
I guess I should move to the next speaker. The next one is time is clicking. Yeah.
Thank you, sir.
Yes, if you just give me a second, I'm going to share my screen now. Okay. Can you see my screen now?
Yes.
So you can see the slides. Awesome. So may I begin now?
Yes, you may.
Sure. Sorry, just something happened. Okay. Okay, good. Hi, everyone. I'm Sepehr Abbasi-Zadeh from University of Toronto. And today I'm going to present our work on application-aware migration protocols in SDN. But sorry, just give me a sec. I just realized something. Okay, good. So by now, it is well established that in the context of SDN, a distributed control plane is required to address the classical issues with a centralized architecture. To name some of these problems, the first and the most obvious one is being a single point of failure. Then we have the scalability issue. We don't want our controller to become a bottleneck either in communication or computation. Last but not least, geographic dispersion affects the delay. So distributing the control plane helps us to avoid unnecessary long distance communications. In the last few years, different distributed control platforms are introduced. But we should note that as the traffic conditions change, some controllers become highly loaded. Also, considering that the network's performance is a function of controllers load, a load or offloading a mechanism for the controllers seems to be necessary. In response to this need, we employ migration mechanisms. First, let me show you a migration with a pictorial example. Let us assume that we have two unbalanced controllers where the first controller is highly loaded, the controller on the left. In this example, we can offload controller 1 by migrating this switch from controller 1 to controller 2. So this is going to be the situation after the migration. While the switch and controller are disconnected, the migration protocol is responsible for taking care of such a safe and reliable handover without losing the state. In this study, we aim at designing efficient migration protocols. There are numerous examples of studies on traffic load migration. However, they usually focus on master and slave symmetric role exchange. The main question that we ask is whether supporting this limited role exchange is enough or not. For example, consider the following scenario. Here, there are two switches S1 and S2, as well as two controllers C1 and C2. And C1 plays the role of equal for this switch and also master for switch S2. And controller 2 is playing the role of a slave for both of these switches. To compare the loads, I should mention that according to OpenFlow's specifications, the slave controller receives only a part of the controlling messages. I mean, just a part of the controlling messages that we are sending to the master and equal connections. Therefore, the load on this controller C2, which hosts two slave connections, sorry. So for this one, the load on controller C2 is much higher, much lower. To balance the load on these two controllers, there are two options. The first option, which I call it the traditional approach, is going to change the role of master and a slave. So here, if we focus on this switch S2, for example, we have one master and also one slave connection. So we could change these two connections. And as I said, because we assume master and equal connections are the major resource of load on these controllers. Here, after this migration, we have achieved the balances that we were looking for. But there's also another approach that we are proposing in this paper, and it is about the role exchange between equal and a slave. So if you consider this switch S1 now, we can do the same exchange, but this time here we are gonna change this equal connection with this slave one. Okay. So again, the load on these two controllers is balanced, but there is a big difference between these two approaches, and that's the fact that here in this new approach, we didn't touch the master connection. So if for any reason, for example, this switch S2 is needed to continue its operation, with this new approach, we have this opportunity to avoid migrating switch S2 and do the same migration with the same goal instead on switch S1. And I want to emphasize on this because throughout the migration, for a short period of time, this switch becomes irresponsive to the requests that it receives. So that's why it is important to have this flexibility to choose between these migrations, which is something that we didn't have before with the traditional approach. Okay, the scenario that I just explained brings up the need for an application-aware migration plan, and also the fact that load balancing is not the only application of interest. For example, in power saving scenarios, unlike the load balancing scenario, we have some lightly loaded controllers, and we want to move away traffic from them so that we can turn them off. For example, here we want to move traffic from controller 2 to controller 1, and in this way we can easily turn this controller 2 off. So in this specific application, at least the load on the source controller is relatively lower than the load balancing application. This application level knowledge provides a better understanding on the requirements and can be of a great help for choosing the fastest and the most appropriate migration protocol. To name the other applications, I can name security concerns, failure recovery, network monitoring, and also controller update and maintenance. So the idea is that if we consider the underlying application that has caused the migration, we can come up with better response plans. To do so, we introduce 4 new protocols. In the first one, we have one initial master which demotes itself to an equal mode, and another slave controls becomes the master. Note that in this protocol, the load on the initial master won't change. So it is mostly suitable for resource reallocation purposes. And in the second protocol, which is actually the one that we're using in our experiments, we're symmetrically exchanging the roles between an equal and also an slave. And in this one, we don't touch the master connection as well, as I mentioned before. And then we have the third protocol in which one initial master becomes a slave at the end of this migration, and another equal takes the responsibility of the master. Here, the master's responsibility handover is being done much faster because the equal controller already has this state. So it is faster to take the responsibility of the master. And in the last protocol, we have a symmetric master and equal role exchange. Now it's time to see the evaluations. We use the same load balancing scenario that we described earlier. So controller 1 is highly loaded by 2 equal and master connections. So we want to move some load from this controller to the other one. And for the protocol, we use the second protocol that does a symmetric change between an equal and a slave. Finally, the question that we want to answer is basically to measure the finishing time of the protocols in test. And as for the baselines, we use the 4-phase protocol by Dixit et al. And the optimized ERC protocol by Beiruti and Ganjali. Note that these 2 protocols were designed to change the master and the slave roles. So we need some modifications in the sent messages contents. However, we don't touch the protocol's structure at all. The testbed is implemented on top of Mininet. We assume that we have 2 controllers that are either in equal or slave modes for some switches of interest. And the goal is to move some load away from the first highly loaded controller to the other one. For that, we change the slave and equal responsibilities for switch S1. Okay, and we assume each of these switches are going to impose the same load on each of these controllers. So this way we can control the total load on each controller by changing this variable n, which is the total number of switches connected to this controller. And in order to generate the traffic to these controllers, we use DITG as our traffic generator. So this is just a simulation, and we're not using an actual distributed controller plane. By running this experiment on different loads imposed on the source controller, we can see that the newly proposed protocol outperforms the other non-specialized protocols by up to 30%. And more importantly, the advantage is on the advantage is higher on heavier loads. Note that even though we call the 4-phase protocol throughout we call the 4-phase protocol 4-phase, throughout our modifications, we completely ignored one of its phases to make it appropriate for our role change. So that's why this 4-phase protocol outperforms ERC's 3-phase protocol. To conclude my arguments, these results suggest that an application-aware design protocol can contribute to the agility of the network, to the control plane to a large extent, and can be considered in the future migration protocol designs. Thank you. So yeah, I'll be here for this poster till the next 20 minutes, I guess, or 15 minutes. So feel free to ask me any questions if you have.
Just one question.
Sure.
I think your migration algorithm or the mechanism is straightforward. Do you consider any challenge here? I mean, it's very straightforward. Anything can bring difficulty or some problems here.
That's a good point, actually. I mean, these protocols seem straightforward. I agree, but you should note that, I mean, these newly proposed protocols have some functionalities that the previous protocols didn't have. For example, we are failure resilient. So if throughout the migration, any of these instances fail, so we can revert the migration and I mean stop the process. Also, we have another feature, which is the consistency. So if you look at these protocols here, for example, we keep other controller instances which are responsible for this switch in a consistent view of the network. And I mean, we achieved this by a buffering mechanism. As you said, these are all straightforward solutions, but it was not addressed in the SDN migration protocols that we had before. For example, this 4-phase protocol that we use as our baseline was one of, was basically the main building block that everyone was using before this. But here, what we're saying is that by using this new approach, we can get much higher advantages throughout, in the control plane of our network. And that's why we're considering these different role exchanges as, again, we're saying that different scenarios need different protocols to deal with the situation. Yeah, our proof for this is just these experiments which are showing how these newly proposed protocols can outperform the previous ones.
So if you want to deploy this in the real system, is there any challenge?
Not at all. I mean, for example, if we consider a distributed control plane like ONUS, the only place that we have to modify is its fault handling module. So there we only need to implement these protocols, and from there, the distributed control plane itself is going to take the control and handle each of these migrations.
Mm-hmm. Okay. Sounds good.
So.
We are the only 2 participants in this session now.
Oh, really?
Yeah, the other is the Zoom manager.
I see.
Francisco is the Zoom manager. So I thought there are some other papers or posters in this session, right?
There is also another one, but I guess I have to start it at 10:30 at my time. So I guess I need to wait for another 7 minutes if that's okay with you.
Yeah, sure. But you know, if there's nobody here, it's rather strange. At least they should show up here, right?
That's true. I mean, that's always the problem that I have with the poster sessions, right? Even if it wasn't a COVID situation.
No, in general, I have the feeling this conference being online and charging so high is a little bit tricky.
Right.
So most of the conferences, when you go online, becomes nearly zero cost. And here you impose so much cost, then there are not many people except authors attending.
Right. That's true. Yeah.
So if we wanted to keep our society to be healthier, it would be much better to open the registration to all undergraduate students or whoever interested, right?
I agree. That's correct. Yeah.
Yeah. I mean, it's my first so low participant ICMP ever.
I see. Right.
Yeah,
Yeah.
and also compare with the other online virtual conference I attended this year, this is also the lowest participants.
Right. I guess one of the reasons could be the fact that the conference itself is being held in a hybrid mode. So, I mean, maybe the timing couldn't be optimized better.
It make any sense to make it as a hybrid mode for this year.
That's what I mean, right? Yeah, I mean, what I'm saying is that since it is hybrid, we have to be, we have to attend these meetings at Spain's time, Europe's time. So at least for me, that I'm in Canada, it's extremely hard for me to attend the meetings at 4:30.
No. Nobody is traveling to Madrid for this meeting. No, only the local people are a few, but I don't think it's going to happen anywhere because today I heard the whole Spanish infected people are about 900,000 reaching this day.
That's insane. Yeah.
Yeah. That's incredible, right? The highest number in Europe.
Yeah, it's overwhelming. I don't know.
What do you mean by master and slave here? I mean, I don't read the migration protocols at all. And what do you mean by equal? Equal means like a peer-to-peer way, right?
Well, I mean, if I want to be, I try to be exact, but according to OpenFlow's specifications, we consider these roles for different scenarios. For example, the master itself is the one who is always answering all the requests from the hosts, from the switches, right? So, but equal at the same time is going to receive all those requests, but it doesn't have the privilege to answer those requests. So that's why we are saying that the master and equal are gonna receive almost the same load, right? Because the majority of the messages that we are receiving in the controllers are called packet in messages, and packet in message is basically the message in which we ask what is the next hop. But I mean, uh, for the slave controller, the situation is different. We are not sending these packet in messages, so they're only receiving a part of these controlling messages. That's why the load on the slave controller is much lower, and yeah, but that's, I mean, that's just a terminology that we're using to just to differentiate the responsibilities.
I just curious if you have such a brand new protocol design and evaluation, why didn't you get it in somewhere visible venue with without the poster, right?
Right, that's a good point. I mean, actually, the first protocol, I mean, we have 5 protocols. These 4 protocols are just the new ones that we are introducing here. But the main one won the NOMS Best Paper Award this year. So what we are doing now is that we want to come up with more sophisticated experiment plans to be able to better show the advantage of this new approach. So that's why we just wanted to expose ourselves and also expose the others with the idea. And yeah, hopefully with these discussions, I mean, we can come up with better ideas to improve the results.
I mean, you should keep eyes on that, how you can improve your own stuff in different situations so that all the potential comments can be previously addressed before you submit the paper, right?
Right, that's also another good question.
That's why I'm asking, do you consider any challenge here? But you say everything is resolved. So I just wonder why, if it is already a perfect solution and well evaluated, why you come with the poster here? It's no use, right?
Right. Yeah, I mean, another dimension of the work that we are planning to work on is actually related to the next poster that I'm going to talk about. So, I mean, now we have these new building blocks. The question is how to use them. So the scheduling itself is going to come into the play. And the idea is to not view the problem as choosing the right migration and then try to schedule those. The idea is to do all of them together, and hopefully with this optimized algorithm which combines these 2 steps together, we are hoping to achieve even better results in terms of the migration time, and also combining with the scheduler, the total migration time if we have multiple migrations at the same time. So yeah, but I guess this needs, I mean, I guess it's better to describe the other scheduling project as well, then maybe you get a better idea of the whole picture.
Okay, good.
And I guess that's the time. So let me switch my screen.
One second. This is Mr. Mancuso. Hi, I'm one of the organizers here. You are staying, so that doesn't matter if you take 5 minutes more on one or the other paper. It's the same. So I just arrived, so I didn't see what you presented exactly, but I wanted to ask you a question. In the migration here, in the master slave migration, whatever, or equal slave migration, have you considered distributed approaches with maybe mobile edge computing or cloud computing versus migration within the same machine or the same cluster of machine? Is there a basic difference in those cases, apart from delay?
You mean the difference between the migration, for example, in a cloud environment versus a migration in our setting, which is the control plane, right? Is that your question?
Could be, yeah, for instance, or in the edge, which could be
Right,
another.
right. Yeah, I mean, all of those situations involve, I mean, different scenarios. For example, in the VM migration, usually the migration time itself is, I mean, it is of course important, but I mean, the order of optimization that we are doing here, I assume, is not that important there. For example, if the total migration is going to take 1 second here, we are optimizing it to be 0.7 second, for example. And I assume for the VM migration, in which the majority of the time is going to be consumed by copying the whole VM, I guess that's why these migration plans could not be that effective in the other scenarios. But in the in our scenario, which is about being responsive and also being agile as much as possible, this improvement contributes a lot to the agility of the control plane.
I see. That's great. Okay, thanks. I guess the second part of your posters is somehow related. So if you want maybe to switch to that one,
Sure,
we can have more discussion.
Yeah, let me just, I just need to stop sharing to change the tab, and then. Okay, let's switch to this poster. Hi again. So in this one, I'm going to talk about scheduling migrations in software-defined networks. The main focus of this study is on the distributed control planes and the way that traffic is being distributed among controller instances. There is going to be a small overlap in the motivation of a distributed control plane, but let me go over that. So not only in SDN, but in any other centralized platform, we have to respond to some serious challenges, including reliability, scalability, and also performance. And as we just discussed before, SDN's response to these challenges is a distributed control plane. But this means that to maintain the performance, the load should be somehow distributed amongst the controllers. And for that distribution, we use migration protocols. As we said, through a migration, we are shifting one switch's load toward another controller, like this figure on the right. One natural question that we can ask is how many migrations are usually needed? And to be more specific, let's assume that we are considering a load balancing application. To answer this, we should note that each controller is responsible for numerous switches, and therefore one switch's load is negligible with respect to the total load on the controller. As a result, any load balancer needs to migrate more than one switch to achieve its goal. To maintain the agility.
Excuse me, can I interrupt? After all, this is interactive, so allow me to interrupt.
Of course. For sure, yeah.
So, what kind of switches you have in mind here? You are controlling any switch in the network, or core switches, or just access backhaul? What do you have in mind?
we only consider open flow compatible switches. So
yeah, which can be any size. I mean, any kind of switches. So if you
right.
are talking about controlling 10 switches next to the radio access, probably switching one may be enough to load balance. But if you are controlling 100 or 100,000 switches, is much different. That was why.
Exactly. Yeah, that's a good one. We are focusing on. I mean, we don't have any restriction on the size of the network or the number of the switch nodes in our network. So,
Okay.
yep. And yeah, because here I'm trying to claim that each migration. I mean, throughout each plan. I mean, in order to achieve this balancedness, we need more than one switch migrations. That's all I'm trying to say. And this means that in order to handle all of these migrations together, obviously we want to handle them as fast as possible, but the challenge here is that we can't do all of them at once. So why? Because we have some constraints. The first one is being the controller constraints. So we have some limited memory and processing resource on our controllers. And also, we usually don't want to violate some QoS agreements that we have agreed upon. And as each migration causes service interruption in the switches, we can't interrupt all switches together. So that's another reason that we can't do all the migrations together. So we call these ones the controller constraints and the other one QoS constraints. And as a result, in order to save time, we have to schedule and batch the migrations in rounds and run each round after the other one is done. Let's consider the following migration example. So here we have two switches, and we want to migrate both of them to the other controller. But here we have a load of 0.9 on this one and also 0.1 on this one. And this switch is providing services to two groups, G1 and G2, two groups of QoS services. And also the other one is only providing service to group G1. Now let's see the controller constraints. It says that each controller cannot support more than one unit of incoming load. This means that if there was no QoS constraint, we were able to batch both of these migrations together in a single round. However, the QoS constraints are telling us that no more than 0.95 unit of load from each QoS group can be scheduled together. Therefore, we need to schedule these two migrations in two separate rounds. And by the definition, each round is a batch of migrations that can be scheduled concurrently. And our main objective is to minimize the number of the rounds required for running all these migrations without violating any of these constraints that I just mentioned. Okay, so the question, is the question clear? The solution that we propose involves two steps of vectorization. In the first step, let's just focus on migrations and ignore the constraints. We assign a vector to each migration and encode all of its requirements in it. For example, switch S1's destination is C2, and so we put 0.9 in its corresponding element. And the same thing applies to both groups G1 and G2. The situation for the second migration is almost the same, with the difference that this switch does not provide any QoS service on the second group, so we put 0 here. Now we change our focus to the constraint set. Like the migration vectors, we fill the constraint vector with the given thresholds now. So we just put the numbers here. The algorithm that we are using for generating the migration plan is called first fit. Now that we have obtained all the migration vectors as well as the constraint vector, we want to run the first fit algorithm on this instance to see how it works. First, we choose an arbitrary migration vector. Remember that we had two migration vectors, M1 and M2. So first, we choose an arbitrary vector and place it in a bin called round 1. So here we chosen M2 and added it to round 1. Then we take another arbitrary migration vector and search over all the available bins to find a place for it. In this step, it means that we take M1, which is the only remaining migration, and see if we can place it in the bin round 1 or not. Here, the answer is obviously not, as we observed before, because the sum of these two vectors is greater than the constraint vector. So we open another bin called round 2 and place this migration into that bin. And finally, we return these bins as our final schedule for rounds. And to formally state the problem, we assume that we have a set of k migrations n1 to ak, and these are given to us as a set of tuples, which tells us what is the switch in this migration, and also the source and destination of the migration, as well as the weight or the load that this imposes on the controllers. Also, a subset of all the available QS groups on which this switch is serving. Okay. We also have the set of QS groups and their limitations, as well as the set of controller constraints. And what we're looking for is the minimum integer value R. This is going to represent the maximum number of the required rounds, such that there exists a partitioning of S into R. So we want to partition these migrations into R partitions S1 to SR without violating any of the mentioned constraints. Okay. In terms of the hardness of the problem, we show that this problem is NP hard. And to do so, we relax the QS constraints and show that the bin packing problem reduces to our migration problem. This means that an approximate solution should be our best hope. But do we know what is the approximation factor of our used algorithm? And the answer is that there is a folklore result for the general vector bin packing problem that tells us the first fit algorithm produces a D+1 approximation for the D-dimensional vector bin packing. And this automatically means that our solution is also approximated with a factor of size C plus size G plus 1. Now we are ready to see the experiments. So for the data set, we use 100 random experiments, and each consists of 30 switch migrations. Each migration has a random destination, and the destination is chosen from a set of 5 destination controllers. And the load is chosen uniformly random from 0 and 1. We also assume that we have 20 QS constraints, and each switch serves a random subset of these QS groups, and the size of this random subset is chosen is drawn from a normal distribution with mean and variance 6. The only constraint on the constraint vector is that we want to make sure that all the migrations can be done without violating the constraints. Okay, and for the baselines, we used we are comparing our solution with the solution that an integer linear programming formulation gives us. In this OLP, we want to minimize the number of rounds. We have the same approach as before, but here we are imposing an exponential penalty on higher rounds that we are scheduling a migration. So this way, we are encouraging the solver to schedule the migrations in the lowest possible round as possible. Of course, this is not going to be optimal, but we expect it to be a good approximation of the optimal result. And as before, we have the controller resource constraint and also QS constraints. So in this figure, we plot the distribution of the required time for running each algorithm in a logarithmic scale as a function of the number of migrations. The distribution is taken over 100 separate runs. And note that the ILP running times were capped by a predefined number, which increases exponentially as the number of the migrations grows. The reason for this limitation is that for some instances of our data set, it takes even more than 10 hours to return the final schedule with our ILP solver. As you can see, while none of the ILP instances were able to finish in less than 20 milliseconds, the majority of the solutions in the other approach are obtained in a fraction of milliseconds. The other important aspect of this comparison is the quality of the solutions. We observed that in 95% of the experiments, I mean, 95% of these two approaches, the number of the generated rounds were the same. And surprisingly, in the rest of them, our solution was off only by 1 round. Here, I want to finish my presentation with a question, and that's whether is there any missing assumption that we can borrow from our real-world systems to show that our problem is not as hard as the general vector bin packing problem. This way, we might be able to obtain better guarantees in terms of the approximation factor. Good, so I am done. So again, I'll be here for your questions, so feel free to ask me.
I see you are very productive, having so many posters.
Thanks. Yeah, as I said, these
If you can formulate then into a series of related problems so that you can make it a single 1 or 2 solid paper, that will be helpful, right? You don't need to make small submissions here and there.
Right. Yep. I hope so. Yeah. I am hoping that we can improve on the experiment size, because as I said, all of these experiments are now just some simulations. For example, for the previous project, it was done in Mininet, and this one is also just some simulations. For example, the data set that we had here was a random data set, and I assume this this couldn't be considered as a solid experiment, I guess, because usually these random numbers are going to cause some systematic distribution on the output solution as well. So that's why we don't want to only rely on these random data sets. And the next goal is basically to come up with some more realistic assumptions on these loads and also the QS groups. Hopefully this way, I'm not sure, but maybe we can even get better results, because who knows, maybe those instances are better than random instances that we are using now. But yeah, and also it would be much better if we can compare with other baselines, I guess. So if you have any other baseline in mind, either for this one or for the other project, that would be also really appreciated.
Okay, I need to sleep.
Okay, I guess it's the end of this session, so please allow me to stop sharing my screen. Thank you. Bye.
Bye.